You welcome to the stream. Now, yep, I guess it's working. Today we will be continuing over our this topic, understanding ownership. So, in the last chapter, we saw right when we want to call a function, we had to pass the string and take its ownership back using this tuple. We don't have to do that. So, how we are going to do is we are going to use it an ampersand. What this sign does is that ampersands are references. So instead of passing this like the whole string and its ownership, it passed just a reference for it. So here we are passing the reference to s1, and as we are passing only reference, not the actual thing and not the ownership, we don't have to worry about getting it back, right? So if we run it, it should work just fine. Yeah. So if we want to represent it with a diagram, this will look like this. Here S is reference to S1, which we created using ampersand sign. We are not referring to here. We are just using the reference to this. You can take a closer look at this. The ampersand S1 syntax let us create a reference that refers to the value of S1, but it doesn't own it. Right? If you have something like, let's say, you have your notebook. I can refer to your notebook, but I can't own it if I am just referring to it, right? Unless you directly give it to me and hey, take this. Instead, you are just telling me that you can refer from my notebook. So that's how the reference is working. And when we are, and last time we just say S is going to be string type, but this time as we are not taking the string, we are just taking its reference. So we have to specify this and string type ampersand for it's for saying that it is a reference. And now you can see the what happens is this s is a reference and it will come in scope, and here s will go out of scope, but it doesn't have the ownership of that original string, so nothing will happen, right? And that's how the references are working. But as we saw, variables are of two types, like they are immutable by default and we can make them mutable if you want to change them. Same thing is with references. If you want to change something from its reference, we have to make it mutable. Like here, if we did it like this, it will just give us error. Like, and help is consider changing this to be mutable reference. And compiler actually tells us what should we do. So here, instead of just passing it as a reference, we are saying it is a mutable reference. Instead of just ampersand, we are using ampersand mute and then the variable name. And notice that we also declare the variable as mutable. So as we saw, variables are immutable or mutable. Same goes with the references. They can be either mutable or immutable. Here. So if we run this should compile and print hello world. Oh, sorry. Actually, we are not printing anything. That's why it didn't print. We can just change this function and try to print it here. So Rust Playground. I just like Rust Playground because if you are not having Rust installed, you can just play with it here. Print line, and we want to print here will be placeholder, and we want to print S. So if I run this, you can see it says hello world. This is just the syntax to change the string, like push the string on the stack. We will see about them in later chapters because we don't worry much about them. We are now focusing on the mutable references. But you can't have like two mutable references. Like we are creating first to be mutable of s, second also mutable reference of s. You might say like, why there can't be two mutable references? Because if you should be familiar with data races, and if you are not, they are like, you know, so other things change them before the one is finished access with, like, kind of like two processes are racing to access that data, if I say in that terms. So if you have like two mutable references, R2 can change the value in between when R1 is not finished yet. So instead of worrying about that, Rust compiler just won't let you to have multiple mutable references. So this will prevent us from data races. And you can see here the benefit of having this restriction in Rust can prevent races at compile time. A data race is similar to a race condition and happens when these three behaviors occur. Two or more pointers access data at same time, and at least one of the pointer is writing to the data. And there is literally no mechanism to synchronize them, right? They are just writing and one is reading, and it can mess up everything. Rust compiler will just prevent that. And by when I say you can't have multiple mutable references, I mean can't have multiple references inside one scope. Like here, you can say this example. This scope, when R1 goes out of scope, we can make another mutable reference without any issues, right? And same rule goes with mutable and immutable combined. Like if you have, we can have multiple immutable references because the data is not going to change as it is immutable, right? So we can read how much we want. But when we make it mutable with immutable, R2 might think that the data is not going to change. And we are saying R3 is mutable, so data might change. This doesn't make any sense, right? One is saying data won't change, one is saying it will change. We can't do that. And those will, if we were able to do it will just be memory issues. So it's better to not do them, even in other languages. And Rust compiler just helps us with it. It won't just compile if we messed up with these things. And same with this, like we can have mutable reference once the first one gets out of scope. Here is the same thing, right? We are creating the references. These are immutable. And once we are printing them, we are not using them R1 and R2 after this point. Then we can create R3. Here, in this example, we created R3 and then again, after creating a mutable reference, we are again using the immutable references. We can't do that, but once we are finished with immutable, we can create mutable reference. So instead of thinking like, we can just say like R1 and R2 says data won't change and they are printing and their job is done. Now we can say data will change now. It is mutable, so it can mutate. So okay, that's fine. We don't have this worry about them because we are not actually using them anymore. So that's how it works. And they are saying, even though borrowing errors may be frustrating at times, remember that it's Rust compiler pointing out a potential bug early, right? If you do this in any other language and you can't spot it unless you have some, like, if you can't spot it and you compile the code and it's running, it will be very hard to track the bug, like where it was and where you are fixing them, and which is not good. And in languages with pointer, it's easy to create a dangling pointer also. This is about dangling pointer. So suppose we have like a reference, we created a reference here. We said let's s be the string and we are trying to return its reference, right? But we know it doesn't transfer the ownership, right? So when we return the reference, here s gets dropped because the scope is over. S will get dropped. So we are basically returning reference to nothing, and which is again considering the memory issues is not good. So that's what it is telling. Here, dangle refers a reference to a string. Like this dangle function is saying that it will return a reference to a string. We declared a new string and we return the reference to string s, which was there. But once it goes out of scope, it is dropped and the memory goes away. So it is very dangerous, right? Because we don't know what will be at that memory address. It can be pointing to anything. We can't just blindly use it. So, and compiler stops us from doing that. We can't just have them like this. You can say here, if you want like what are dangling references and why they are bad, you can read this. But yeah, if you want to return a string directly, you can return a string like directly, that its ownership will be moved and it won't be deallocated after the function is over. But you can't just return a reference to like nothing, you know. And here are the, it's like the recap for our chapter. At any time, you can have either one mutable reference or any number of immutable. And a reference must be valid. It can't be like invalid references pointing to anywhere. We call them as dangling. And now we will take a look at another type that doesn't have ownership, which is slice. So here you can see slice let you reference a contiguous sequence in element in a collection rather than a whole collection. Like instead of pointing at the whole string, it will let us point at some particular section of a string, right? So here is a small programming problem. Write a function that takes a string and returns the first word it finds in that string. If the function doesn't find a space in the string, the whole string must be one word. So entire string should be returned. So we are just returning like the first word from the string. So what will be the first word? It will be the, so here in hello word, first word will be this hello, because after that it is space, and then word will be second word, like this. So here we wrote a function. We called it s.sbyte because s is a string element and we want to convert it in bytes. So we convert it to array of bytes by using asbytes function. So we can compare them easily. That's why we are doing this. And then for we are using this iter. We saw that we use iter to create an iterable object from that bytes. The array of bytes we are making an iterable and we are calling enumerate. So it will take note of that index and as well as the atom. We will see about this syntax and all this in more details in chapter 13, where we discuss iterators and enumerators in like bit more deep depth. So here it is explaining why it uses the ampersand pattern, but it is just because how the enumerate function use. We are for now concerned about the slice type, so we are focusing on that. And then we are comparing that if item is white space, we just return the index, right? Like at the index we found. And if we didn't hit this if condition, that means we never saw any space. So the ending of the string is the end of the word. So if I just here, if you run it on this, it will just iterate over this all. After comma, it will see there is a white space and it will return the index of the white space. And if there was no white space, like suppose this is the word execution, it will iterate over this, but it didn't find any white space, so it will return the size of this word. That's how it is working. So here, now this was our function called first word. Now let's see we want to use it, right? So what will happen here? Here is the function. They are just hiding it, just in case you know. This will get the value of 5 as, because this will be considered as a one word, and it will return the index of the space. Here it will return this, and s dot clear is like a method on string which creates, which clears it. So our string now will be equal to this, and you can see the comment here, word still has value 5 here because we assigned the value 5 to the word, but string, but there is no string, right? So that we could meaningfully use that 5 weight. We want to return the word, not just the index of that word. But here we cleared the string. What are we going to do with 5? Like, we know that the space was at index 5 and we have to return the words, the letters before that in the word, but we don't have the string anymore. And you can also do it for the second word. Here, see, having to worry about the index word getting out of sync with the data in S is tedious and error prone. Managing this index is even more brittle if you write a second word. Like if you add a second word, it will be, more error prone. And they are explaining it here. But we have a solution for this. It is called string slices. So what string slice is? It is like a reference to a part of string, not the whole string. So when we say here, we are saying and s ampersand s, and then we are using syntax like arrays here, like square brackets, and specifying a range here, where the first is starting index and then dot dot for range, as we saw in for loops also, and then there is ending index. So it is basically a range, like it will start from 0 till the 5th. So it will be 0 1 2 3 4, and as we saw, after dot dot there is no equal sign, so 5 will be excluded, so the word will be hello. And then for the word, we are going from 6 to 11, so 6 7 8 9 10, and there is no equal, so 11 will be excluded. So it's like 6 to the last of thing. And if you want to see the diagram, this is how it looks like. Our word which we are saying from 6 to 11, it will be pointing to 6 and length will be 5, so it will be 6 to this 5. This is how, this is the, what we say, string slice working. And one thing to know, that string slice doesn't take any ownership from anyone. That's what the starting line of the chapter was. It doesn't have ownership, like it won't take ownership from S. So, and we can just skip the first index, like we can just say like dot dot 2, it will be same as string from 0 to 2. We can just say this dot dot 2, which will consider it like starting from the first index, and same goes with the last index. We can, if we want, we can specify the last index, or we can just skip it, so it will just take till the end. And we can also drop both values. We can just specify dot dot, so it will be the whole thing. And here is note that string slice range indices must occur at validity of 8 character boundaries. And this is like, we can use multi characters and all that, but for now we are just dealing with ASCII text only, so we don't have to really worry about them right now. And now here, as we saw in first word function, first we are just trying to return the index of the word where we found the word, and then we add nothing, right? Then we can't really do anything with that index afterwards. But here we can just specify that this function will return a and string. So we can say like string slice is written, string slice is also written as this ampersand str, like we saw in string literal. So we are doing basically the same thing, but if we found a white space, we are saying return from the zeroth index till excluding till the index where we found a white space. And if we don't find any white space, we are just returning the whole string as a string slice. So that's how you will specify if your function returns a string slice, ampersand str. And you can see here, we declared a string and then said then we passed our string to this first word function and then we called clear. But there was an error. So what was it? You can read it here. We now have a straightforward API and that code was logically incorrect but didn't show any immediate error. Problem show up later. So let's see what the problem was. Here we are immutably borrowing this and mutable borrow here. When we clear this, we are mutably borrowing it. And we saw like we remember that we can't have like multiple um, like immutable and mutable borrows at once because clear needs to cut the string. It needs a mutable reference and Rust will disallow that. So this is just thing to note that we were just what we are doing here, we were getting a 5 here, the count for the word, and then we are easily clearing the string, and now we don't have the string which we like, we don't can't relate the string with the 5 by any means. But here, even when we got the string literal, we can't change the string, we can't just like clear the string so it don't match with the words, nothing will happen like that. So this is how it will eliminate those bugs too. And here string literals are also slices, like we just specify them like that and we said they are not, they are immutable, they are also string slices. And as we were returning from the function, we can also pass it as a argument to the function. So here, if we saw here, instead of passing the string, we are just passing the string slice of the whole string. Same is with here, we are passing the whole string slice. And because string returns are string slices already, this works too without the slice syntax. And you know we just saw that the string literals which we declare are also string slices, so we can just pass them without this ampersand and this syntax. We can just pass them like this. There are other types of slices also, like if there is an array of integers, we can use this slice, but this won't be string slice, it will be of type ampersand I32 instead of string, and which we will discuss in later chapters. But this is how the concept of ownership, borrowing, and slices ensure the memory safety in Rust programs at compile time only. We don't have to spend hours debugging them and to find where it was going wrong and where is the data race and all that. The Rust language gives you control over your memory just in same way as any other system programming languages. But having the owner of data automatically clean it up that data when the owner goes out of scope means that you don't have to write and debug extra code to get this control. And ownership will affect like lot of things. We just saw the basic programs here, but it will affect the other things when we declare structs and all, implement them, but we will see about them in later chapters. For now, if you have anything to ask, you can ask in chat, like if there is anything. Okay, if not, then I will just end the stream. Here you can see. Okay then. See you tomorrow.